So this session is on the so-called distributed deep learning. So what I'm going to do, I will give a short presentation just to have some kind of conceptual understanding about what is distributed deep learning. And then later on, we'll go through these tutorial examples so you can, try some simple example to learn this how to do things on Polaris. And let me of course I'm assuming that right now we're kind of everybody is coming from HPC with certain HPC background, deep learning background, right? So the why we need to do distributed training essentially, because the model become larger and larger, the amount of compute in the model increase exponentially. And so you can see this is the plot from OpenAI a few years ago. And what it does that it calculate the amount of compute in each of the model that in the literature, ranging from the most simple model proposed in 2012 for ImageNet problem. This is AlexNet. And then it just exponentially increase, like, AlphaGo 0. This y-axis is the petaflop per second day times day. So that means if you have a petaflop per second machine, it will run 1 day in order to finish. For example, if it is one, right? VGG model will take a petaflop per second machine run for 1 day, and 1,000 will take a exaflop machine to run for 1 day. That's the complexity of the model, right? So, and historically, of course, initially people just do things on a single GPU, and now more and more people doing at large scale because of the model complexity. And just give you an idea about this ResNet 50, which is an ImageNet model. And if you train this on a single NVIDIA GPU, it will take about 2 weeks. But if you train on Summit, the current machine at Oak Ridge, it will like fastest one, it will take about like less than 1 second. This is for the training part, right? Of course, when you really run this model, it will have initialization, loading the data, etc. It will take a little bit more than 1 second, but you can get an idea about the speed up. And so the goal of this tutorial today is first, we want you to understand the the distributed data parallel, and we'll compare with this model parallelism and data parallelism. And then really, we hope that you can just modify your code with Huihuo. We provide 2 examples that you can just modify the code, which is initially is a sequential code running on a single GPU, and you can kind of modify it with Huihuo, which we'll discuss a little bit more later on, and then try to run it on Polaris. And of course, we'll talk about the frameworks, the software that needed to run distributed training. Yeah, this is basically why we need this. The model increase complexity and the amount of data set also increase. And another reason is right now many group has been implemented surrogate model. Basically, have a deep learning model be embedded into HPC simulation. So there's a coupling between the deep learning and HPC. Since the HPC part is generally done in large scale distributed fashion, therefore it's crucial to make the deep learning model also run in large scale. And in generally, there are 2 big kind of categories of parallelization schemes. And there's some hybrid mode in between of these 2. But once we understand this tool, then we understand the other kind of more complicated ones. The first one is the model parallelizations. So basically you have a big model composed a lot of neurons, right? And then what we want to do is that we just partition the model, and then like some part of the worker, you can think about the worker as a GPU. So basically there's 3 run belongs to GPU1, and then there's GPU2, GPU3, GPU4, 4 GPU working together. And so the model is partitioned into 4 parts, feed into different GPU, and the data continually feed, right? So this is a model parallelization, just divide the model and then put it into different part of the GPU. And then every time when we think about the parallelization, we'll care about the communication overhead. Means the data flow among the different workers. So in this, you can see that the data flow is basically the weights, the output, like the output of worker 1 flow into worker 2 and worker 2 as the input, right? So you can think the model parallelization in this case has kind of slightly less communication overhead compared to data parallelization, which I will talk later on here. So the data parallelization is we duplicate the model, and each worker has a complete set of neurons, the complete model, but we partition the data into different subset. And you can think about basically each worker only process a subset of the data set, right? So that's how the parallelization or the scaling efficiency become achieved, right? And there is also a communication overhead involved. Basically, all this model has to be in sync throughout the whole training period of time. So basically, each time it process one batch of data, then you have to, because of the different worker have different subset of the data set, therefore they update the model. The local weight will be different. So in order to that then keep in sync, we have to average the weight and loss across all the workers. And that's the communication that's involved, which is the collective Mpi or reduce. And so you can compare this to, like, this is a kind of more neighborhood communication. This is a collective communication, right? So in terms of the communication overhead, I would say that data parallelization typically is a little bit higher than this. But from the simplicity point of view, this data parallelization is very easy to implement and very easy to do the load balance. Like different workers will have basically the same amount of work, whereas the model parallelization, it's relatively hard to partition the model into a kind of relatively similar size of different partitions in order to reduce the load balance, right? On the other hand, regarding this memory footprint, this data parallelization, because we put entire model in a single worker, so the memory footprint or memory consumption of the model is higher. It's higher than the model parallelization. So for very, very big model, you might not be able to fit a model into a single GPU. In that case, you have to do model parallelization. And there are some framework that can do model parallelization. And also besides this tool, there are also pipeline parallelization, which won't go into too much detail. You can always Google it and learn more about it later. And then this, this should be the model parallelization. A little bit kind of deep dive is that basically in the machine learning training, right, what we have is a loss, and this loss is calculated with summation with respect to different data set, right? So you sum over the loss and you get the global total loss. And this W is the weight or this parameter of the model. And basically during the training, we update the weights, the parameter in the model in order to minimize the total loss. And the algorithm is used is called stochastic gradient descent. So instead of so it basically calculates the gradient of the loss, but this loss is not the total summation of the loss, but actually just the loss with respect to one batch of the data, So with that, one batch of the data, calculating this loss, and then update the grade, update this the weight at each step. And again, this is easier to parallelize. Basically, we can kind of have a mini batch, and then say that we have 100 sample in that batch, right? And we can have 10 workers to work on that mini batch. Basically, each worker will work on 10 batch. So we will divide the mini batch into sub mini batches, and each sub mini batches into each sub mini batch fit into one worker, right? And then at the end of this one mini batch, which is a one training step, then we do the or reduce. So this is basically the whole framework, and there are some thing we need to change. First is the so-called linear scaling rule. Basically, in the training we have a variable called learning rate, right? This is basically how much is the step you jump in the optimization, and I won't go into too much in the mathematical detail, but basically when we scale the model, we'll have to multiply this scale this learning rate also proportionally, so that if we have twice the number of workers, then the learning rate will be twice large. And this will run into a problem called large batch training. And we'll have some tutorial example to show this. But the idea is that if you run on single GPU, the learning rate is small, right? Now, if you run on 1,000 GPU, then the learning rate will be scaled by 1,000 times. And this will become an issue for convergence, because of a large learning rate will introduce a lot of kind of unstable issue, and also there's an issue called generalization gap. So it will have impact on the overall accuracy. If you're interested, you can check this this paper for detail. But there are some way to try to avoid that by using warm-up step. Basically, in the beginning, several epochs, we just use a smaller learning rate, and then only after the training going to a stable phase, then we scale the learning rate. Okay, so all of this are a kind of conceptual things behind this data parallel training. And in terms of software side, is very simple. So what we have here, I list here what we need to do in order to change a serious code into a data parallel code. And we will see this in the real code example later on. But basically, the framework that we used to do data parallel is called Huihuo. And there are other framework called DTP, which is very good for PyTorch, which we'll also touch about briefly in the tutorial examples. And then also DeepSpeed, which is very popular in the natural language processing models world. But here I want to kind of focus on the Huihuo, but the general idea are kind of pretty similar among all the different framework. Once you learn one well, then you're able to kind of do things with other framework also. So basically, the first step, you need to import a Huihuo module and then initialize the Huihuo. This is like a MPI init in your traditional HPC code, and then wrap this optimizer with the distributed optimizer. So what the optimizer is doing is it calculate the gradient of the loss, right? Calculate all the gradients. When we wrap it with the distributed optimizer, it will not only calculate the local gradient, but also average among all the workers. So this is what it does at this step. And then scale the linear rate, as I already mentioned, and broadcast the weights from the worker 0 to all the workers. This is to keep all the workers have the same starting point. And then later on, of course, through the all reduce, they will at each step they will be synced together to have the same model. And if you have checkpoint, you will just want one worker to do the checkpointing. Okay, so this is kind of very simple. There's steps, and you can see how change the code make change in the code. There's also another part. It's just the data loading part. Since in the data parallel training, each worker only work on a subset of the data, right? So we need to kind of short the data or divide the data into different partitions. And if you use the PyTorch or TensorFlow, they have their data loader, and the data loader provides a way for you to shop the data set. We can see more in the example. And this is just an example that we did before with Theta run the Resonance 50 model up to 2000 KNL nodes. And you can see we can get like this, the white box is the ideal scaling. This is the image per second, the throughput, training throughput. So you can see we can get about like 50% scaling efficiency running up to 2000 nodes with Huihuo. We have more recent result with the Prioros, which I didn't include here. Okay, so and we can also do Mpi profiling, like where does the time go in all the Mpi communication, and you see this is done on the CPU side, and we found that indeed the communication happens more on the MPI reduce. You can see majority of the communication happens here. Okay, so up to this point, I can take some question if you have any question. Can put on the Slack, maybe some other of my colleague can answer, or if you just unmute yourself, I can take one question. Okay, I assume no. So let me go to the example. Okay, yeah, this is the GitHub repo. If you have that on the priorities, please do git pull to pull the recent change. And this is under the distributed deep learning. And we here provide example of Huihuo and DDP and deep speed. You can see all the example, but today I will mostly focus on Huihuo and touch briefly on DDP. Okay, so if you go to the Huihuo, these are all the things that are already mentioned in the slides. And here you can see the example of how to make change to the code. For example, we can go through one example with TensorFlow. First step, just initialize the Huihuo, load the modular, and do the Huihuo init. This will kind of set up the communicator like MPI init that I mentioned. And then with this, you can call this Huihuo rank, Huihuo size, and to get the rank ID and the total number of processors of your communicator. And then the second step is to assign GPU to to each rank. So in this case, we call this Horova local rank is a local ID. Like it will on Polaris, we have 4 GPU, and suppose we run the 4 ranks per node. This will run from 0, 1, 2, 3, and then 0, 1, 2, 3. This, and so we basically ping that each GPU be pinned with to 1 rank. And then this is to wrap the optimizer. And actually, TensorFlow provide another way is not wrap the optimizer, but wrap the gradient tape. You can see all the code example later on. And then broadcast the model and the optimizer variable to other from worker 0 to other worker, and then checkpointing to avoid like different ranks writing the data to the same file. So we just let only rank 0 do the checkpointing, right? And then loading the data according to the rank ID and just the number of time step. This is what I mentioned, that you partition the data set into different subset. Both TensorFlow and PyTorch provide a data loader, provide a function in the data loader for you to do that. And then average, this is also important. When we have the loss and accuracy, we want to average among all the workers and to at the end to report, right, as the metrics. And also other example like Keras, PyTorch, and you can check for detail. So later on today, or if later on you have some time, I provide these 2 example, PyTorch MNIX. This is a series code without Horova. This is also a series code, but with TensorFlow without Horova. And you can just follow all these steps. And once you do it once, then you know how to do it. If you just follow, I used to just follow step by step, kind of on the fly, but it's good to you do it once. Okay. Today I won't just go through it step by step, but you do it once, and you can. Let me reshare to my entire desktop. Inside of the folder, this is the GitHub repo, and go to the folder in the Horova. I provide a lot of Python example. This one is PyTorch example with MNIX, and the one with the original. This is the one without. Let me. Yeah, the left side here. I have 2 panels here. The left panel is without Horova. The right panel is with Horova. So with Horova, so you can just modify this code and then compare with the code that I provided. And if you're able to kind of make it run, then it's very good. It will be very good. And okay, so going back, if we go to the Polaris, now we just want to, maybe later on you can modify the code, but for now, we just want to run those code to get a feeling about like when you run in parallel, how much speed up you can get, etc. So there's some setup that you need to do. Here I use a weights and bias, which is a very good way for us to visualize the results. So what you need to do now is go to, okay, this is the Polaris markdown file, and so you can go to this weights and bias website and register an account with your GitHub and sign in and do this setup. I will just maybe I'll just go through all the results first, and then you can just follow this step by step on your own. So once you get this, then you just export this API key, put in your setup script, and then you can SSH to Polaris, and this is the command to load this modular for the software for the TensorFlow and PyTorch. Okay, it do the QSub. Actually you should do this interactive request. Here you can do all things with 2 nodes. All this example with just 2 nodes. So what I did here is I request a 2 node interactive job, and after I get it, you can load the modular, conduct modular, and activate that, and then you can run this code. So here it is a PyTorch MNIX example, and then running on device GPU, and I turned on the weights and bias lock. So this, once I turned on this option, it will lock all the results, and then also this will be synchronized to the weights and bias website, and you'll be able to visualize the result in weights and bias website. And this is the project name I provided for the weights and bias log, and then this is running with 4 GPU, and so you can also do the scaling test. Example, you run with 1 to 4. Here, I didn't go beyond 1 node. If you go beyond 1 node, there's some issue with the data loader where you cannot do multiple thread to load the data. You have to set the number of worker equal to 0 in order to go beyond 1 node. This is just a currently limitation in our software on Polaris, will be addressed later on. But for now, maybe you can just focus on one GPU to 4 GPU. And then after that, I can show the result that I have in the weights and bias website. So, okay, this is what I have. If you turn on the weights and bias log, and then you go to your weights and bias, and this is the project name I provided, then this is the result. Basically, I output the training loss, test loss for the test data set, training and training accuracy, test accuracy, and then also time per epoch. And I have multiple run here. From one GPU, this is 1 GPU, 2 GPU, 4 GPU. So you can see that this loss and accuracy curve are pretty kind of similar to each other at this small scale. But you can immediately see this time per epoch reduced, right? From the 1 GPU case, 12 seconds to 8 seconds, and then to about 5.7 seconds. It's not a ideal ideally scaling up like twice for 4 times because the model is very small. It's MNIX example. Okay, if you run other larger model, your scaling efficiency will be higher because of the compute part will be more dominant. The communication part will be kind of not too much. So not cause too much trouble in a large model. Okay, so let me go back. Yeah, I also put the time here. Have the Sci-Fast 10 MNIX running from 1 GPU to 4 GPU. So you can see this scaling. Then the other thing that you can try is to see the problem of this so-called generalization, I mean, large batch size training or large learning rate problem, right? As I mentioned before, when we use multiple GPU to train, we have to scale the learning rate, and then this will become a problem if the learning rate is too much. So I show one of the example. It's very easy to play with the TensorFlow. With TensorFlow, it's not as easy to play with the PyTorch. So in this example, in this study, I just used the TensorFlow code that I provided in the GitHub repo. So this is a TF2 and next example. And again, I do one GPU all the way into 8 GPU, and maybe it's easier for me to show interactively on the Wisdom Bias website. So you can see I have a lot of project here, and one of that is, warm up example. This is the example I have. So the nice thing about this Wisdom Bias is that you can, for example, hide this one, hide this one, hide this one. Somehow the update comes. Okay, so this is from 1 GPU to 2 GPU to 4 GPU. You can see, now we don't focus on the time per epoch, but more on the training accuracy and the testing accuracy, and also the training and testing loss. You can see this 1 GPU, the training accuracy is kind of 99%. And then once you increase this number of GPU, the accuracy reduced. Like 4 GPU case, it's 0.94, right? And so it have the impact on this accuracy. And in particular, if I increase to 8 GPU, I purposely put the initial learning rate to be a large learning rate. I think I put the 0.01. So to show this problem. If you use a smaller learning rate, maybe even up to 8 GPU, still it's okay. But I choose a larger learning rate. So basically, the initial learning rate will be 0.01. So if you use 8 GPU, the learning rate will be scaled by 8, a factor of 8, it will be 0.08, right? So when you have the 0.08 learning rate, it becomes an issue. So the training accuracy stay at this 10%, right? 10% is reasonable because we have 10 digit and a random model without being trained will be 10%, will give you 10% accuracy, right? So this will be 10% for both training and testing, right? So no matter how long you train, it doesn't converge. Now, you can do the warm-up epoch. Basically, what I said here is need to wait some point. Okay, so there is a curve. There's let me turn off the other curve. Okay, so just compare this one with the without the warm up and the one with warm up. So you can see with warm up again, I can get like pretty good training accuracy up to 99%, right? Similar to before. Again, for the testing, 98%, pretty good, right? So this warm up epoch, what it does is that I said warm up epoch to 2. So basically in the first 2 epoch, I still keep the learning rate as 0.01. only after the third epoch, I scale the learning rate to 0.08, right? So because of with this first two epoch, the training, the optimization process is already being stabilized. And then after that, I increase the learning rate. It's easier for it to find a good minimum point. But if in the beginning, the learning rate is too large, then it will just keep jumping around and cannot find a good minimum point. So that's the trick that we can use with this warm-up. And then in terms of the code, maybe I can show briefly what I did in the code in order to do this learning rate, warm-up stuff, right? So it's very simple. It's actually, this is a training epoch running iterate from like 0 all the way to 32 epoch, right? 31 epoch. So what I did is that if the epoch is smaller than the warm-up epoch value that I set, this the optimized this learning rate will be this, right? Otherwise, it will be scaled. I will scale that. That's quite simple, yeah. In this TensorFlow, and then yeah, in terms of the code, yeah, it's kind of very simple. If you look at this TensorFlow 2 and next example, and then you search for Horova, I mark the place where I make change in order to make it run with Horova. So here you can see Horova just in the very beginning of your code, load the modular and initialize. This is initialize the Horova, and then you can also check whether you get the correct number of processors and the rank ID, right? And all this part is for weights and bias log. As I mentioned, I only like rank 0 to do all the I/O work, like writing the log, writing the checkpointing stuff. So I put an if statement here. This is pin GPU to the Mpi process, and you can just copy paste from the markdown file I provided in order to make change to your code, like in your research. And this is the loading the data set part. This data set, and then this is sharding of the data set. So if we do data parallel training, we can use this shard in this TF data pipelining. I think maybe Taylor this afternoon will talk about the data pipeline data loader. So maybe you will know more about this. But basically, it just said the how many partition you want to do, and then each rank have their index of the partition. And so this is the setting the data set. This is defining the model. And here I have in the beginning, I wrap the optimizer. Of course, later on I make the change because I want to do the warm up step. And then there's this one is to broadcast in the first step, broadcast all the initial states of the model and the optimizer to other ranks so that all the workers will have the same starting point. Okay. And then when you're in the training loop, you just, this is the doing the training batch by batch, calculating the loss and accuracy and do the average. So this is training loop, and this is the testing or validation, testing loop. And after that, I just also do the average, my order worker, and then print out the training loss and training accuracy. Right. And if I have the weights and bias syndrome, it will log all this to the server. again do the checkpointing with rank 0. So it's very simple. Now we have about 20 minutes. Let me show another thing with the DDP. In terms of this DDP here, the code I also provide is actually this is provided by Corey, and I made some change of the code this morning, just to enable it to use the weights and bias log, and so they also have MNext example and Sci-Fi 10, and in terms of the making how to make the change is very similar to Horova. I won't go into detail, but I do want to show you one thing is the scaling efficiency. So this is again with the Sci-Fi 10 and MNext, and with the two code, and this is the scaling efficiency of this two model, and this is a plot that I kind of show it to you in the Horva case, and this is for the DDP case, for the Sci-Fi 10, and then I want to show you this comparison between this DDP and Horva. So you can see with Sci-Fi 10, both in Sci-Fi 10 and MNext is kind of more obvious, like that is a DDP perform better than MNext, than the Horova for the PyTorch model. And this Sci-Fi 10 is a larger model compared to MNext. So the more communication overhead involved, then DTP will show better improvement compared with the Horova. This is for PyTorch model because DTP only work for PyTorch model. So for PyTorch, I would suggest you to use DTP instead of Horova. But for TensorFlow, you can use both. Their performance probably quite similar to each other. Sorry, TensorFlow you are not allowed to. You cannot use DTP, so you can only use Horova. But the Horova implementation and Horova support in TensorFlow is better than the Horova support in PyTorch. So it in PyTorch it can kind of get quite similar performance when you use PyTorch with DDP. What I mean is TensorFlow plus Horova is you can perform very similar to PyTorch with DDP, right? If your model is the same, and implementation is the same, then this two should get quite similar performance. I'm not sure. Maybe it's yeah, the main reason that this PyTorch or PyTorch DTP is better than Horova is because of Horova, the overlap between the communication and computation, DTP have better support. Okay. I think that's all the results that I have, and so I just go through all of them together. And now you can start to play around on your own. You can go to this Horova case and just follow step by step. Sorry, this is a README, so maybe go to the hands-on example provided at the end. Polaris, the markdown file Polaris. You can just follow step by step, and ask. You can ask question on the slide if you hit any problem. Okay, I will just stop my presentation here, and I can answer the question. maybe I'll just show this tutorial example file. Okay, I'll mute myself and go to Slack to answer the question.